Hello, this is Mr. Collier, and today we're doing the principle of mathematical induction with derivatives. Okay, so we're going to prove this formula for the nth derivative, and in general these always start with n equals 1. So we'll say for n is in z plus, right? So n equals 1 is the first derivative. So when we do n equals 1, we just get the first derivative. So dy dx equals, the derivative of this is just e to the 2x plus 1 times the derivative of 2x plus 1, which is 2. So we have that. And then the left-hand side is going to be 2 to the power of 1 times e times 2 times 1 plus 1. Sorry, x, that's an x, not an n, so this should be x, which equals obviously 2e to the 2x plus 1. Okay, so therefore it's true for n equals 1. So for n equals k, assume dky, so the kth derivative, this is how you write it. Assume the kth derivative equals 2 to the k e to the 2x plus 1 for some k in z plus. Okay, so we always have that kind of step. Now for derivatives, it's pretty easy. This step is always just getting the k plus 1th derivative. So dk plus 1 of y dx k plus 1 equals d by dx of our assumption. So we always do that, find the derivative of your assumption. And then hopefully it'll all work out. So when I find that derivative, this is a constant, so it's differentiating with respect to x. So when I differentiate, I get 2 to the k times e to the k plus 1 times 2 by chain rule. So that 2 times 2 to the k gives me 2 to the k plus 1, and it's e to 2x plus 1. So we're done with that step. That therefore true for n equals k plus 1. And then we can write our sentence at the end. Since it's true for n equals 1, and assuming it's true, or you can write like this, is even easier. N equals k true implies n equals k plus 1 is also true. Then it's true for all, I'll write down the actual statement, 2 to the n, dn y dx n equals 2n e to the 2x plus 1 for all n in z plus by the principle of mathematical induction. Okay, next example. It's asking us to find the first 4 derivatives, so let's list them out. First derivative. By chain rule, you're going to do the derivative of that, which is negative 2 times that, so you're going to have 8 e to the negative 2x, and you find the derivative again, multiply by negative 2, you're going to get negative 16x to the negative 2x, or sorry, e to the negative 2x. And the next derivative, you're going to have 32 e to negative 2x, and then the fourth derivative, that's to be third derivative. The fourth derivative, which you write like that, equals negative 64 e to the negative 2x. Okay, so for part B, derive a formula. Well, firstly, they're alternating between positives and negatives, so we can write that as a negative 1 to the power of something. And if we use n And for the first one, it would be negative, so we need an n plus 1 or an n minus 1. That will give you a positive 1 here, and then negative, and then positive, and then negative. And then we have powers of 2. So it's going to be 2 to the power of something. 2 to the power of n only gives me 2. So it needs to be 2 to the power of n plus 2. And then you always have an e to the negative 2x. So that's the formula. We're going to prove it with the principle of mathematical induction, similar to the previous example. Okay, so we're going to start with n equals 1. And so we have f prime of x equals, what was the original function again? This, right? So it equals 8 e to the negative 2x. And then we can check this side of the formula. So negative 1 to the power of 1 plus 1 times 2 to the power of 1 plus 2 times e to the power of negative 2x does give you 8x, 8e to the negative 2x. So therefore it's true for n equals 1. N equals k, we just write it as, we'll do an f notation, so f k of x equals negative 1 to the power of k plus 1 times 2 to the power of k plus 2 e to the negative 2x for some k in z plus. Okay, now your k plus 1 step. We always just get the k plus 1th derivative. So actually, let's write it like this. Fk plus 1 of x equals dy, or d by dx, the derivative of f of k of x, which equals the derivative of what we had in our assumption, which is negative 1 to the power of k plus 1 times 2 to the k plus 2 e to the negative 2x. Okay, now when I differentiate, that's only with respect to x, so these are constants. So when I find the derivative, it's going to be exactly the same thing, but using chain rule, we have to multiply by an extra negative 2. Now when you multiply by negative 2, that's like multiplying by negative 1 and 2. So I'm going to take my negative 1 and multiply it by this to give me negative 1 to the power of k plus 2. I'm going to take 2 times this to give me 2 to the power of k plus 3. And e to the negative 2x stays the same. I can rewrite it a bit clearer. Write this as k plus 1 and 2 to the k plus 1 plus 2, just to clearly show that this is the k plus 1th term. So therefore it's true for n equals k plus 1. And then you can write your sentence.